But what if the predictor, so in this case, this works kind of clean, and it introduces you to the idea of an odds ratio. I should make a point, obviously that's made up data. An odds ratio of 9 is huge. I mean, that's outrageous. Just made up data to illustrate that. But, and so that kind of introduces us to what the odds ratio is. But what about if our predictor, if you have a predictor that's not a dichotomy, not parent dropped out, didn't drop out. What if my predictor is a continuous variable? You can't, that nice little 2x2 grid won't work for years of parent education. It just works for did they drop out or not. That's where we get logistic regression. Logistic regression, you can do logistic regression with a dichotomous predictor, just like in multiple regression, we could have dichotomous predictors. You can do that with logistic regression, but just like with multiple regression, we can have continuous predictors. In logistic regression, we can have continuous predictors. So let's kind of change our example and think now we have 60 youth. 25 of those kids dropped out of school. 35 went on to graduate. This is a tough neighborhood. Our independent variable is the number of years of schooling that their parent had. How many years of schooling did their parent have? Notice the outcome is still dichotomous. Our outcome is, did the child graduate, yes or no? We're going to code it in the data, 0 meaning no, 1 meaning yes. And that's just kind of you've heard me talk about this before. It's always a clean way of label your variable in a way that 1 means yes. So in this case, the 0, it didn't happen. It's often some negative in the research. It's typically it's often some negative event not happening. You didn't die, you didn't get arrested, you didn't drop out of school is the 0. And the 1 is that something did happen. You died, you got cancer, you got arrested. Okay? And that's the 1, indicating whatever happened did happen. Now we can graph the data. Remember, we always like graphing the data to kind of get a sense of, or do we see anything weird in the distribution? And in this case, you can clearly see something weird in the distribution. I need to redo this and make these dots. The problem is because notice there's like 5, you may not be able to see this, there's like 5 little dots here. It's really 5 dots all right on top of each other. I've just spaced them out a little bit that you can see a frequency for each of these. But kind of what this visually tells you, I've graphed parent education on the x-axis, our predictor, and our outcome is dropping out. They didn't or they did drop out on the y-axis. And you immediately should notice, yeah, there's something weird with this data from a multiple regression perspective. Notice we don't see our nice little lopsided potato cloud of scores. It's there's nothing in between. We only have values on our outcome of 0 and 1. I could plug this into a multiple regression. I've seen people do this sometimes. And that's an easy one if you're a reviewer to catch. It's like, I can't do that. But if I did a multiple regression and put a regression line through this, it's going to look something like this. And SPSS won't care, R won't care that you're doing something ridiculous. It's not that smart to come back and say, I see what you're, Not yet, but I bet you in a few years it'll be kicking out saying, you can't, yeah. At a minimum, kind of making some noise at you, kind of booing or hissing. Yelling insults, that could be fun. If you could program it with insults. What the f are you doing?
That'd be great.
Wouldn't that be great? Yeah. You can personalize it with compliments or insults. Good job. loser. But anyway, so you can put the multiple regression line in, and it doesn't make any sense. If you start to think about it, you can see all sorts of problems. Notice that the errors are going to be really screwed up. That very small errors, then no, you know, if here's our predicted score, so it'd be a lot of scores very close to the average, to their predicted value here, and then a couple that are way off. And then some that are kind of off on both sides, and at the other end, here's some that are very close to the average and way off in the other direction. So the errors are very heteroscedastic. They're not kind of, the size of the errors is really going to vary across parent education. They're definitely not going to be normally distributed. You know, even beyond that, you got a more fundamental question of what do these numbers, what does the regression line even mean? I mean, it's our predicted scores, right? Well, what happens if you plug in a predicted score for 16 and you end up getting a dropout score of negative 0.7? What does a negative 0.7 mean? Or a dropout score of positive 1.4? The numbers are outside of any range of meaningfulness. So that doesn't work. You can't do that. We need to do something with those scores to make them more analyzable. Well, we could convert them to probabilities. And the kind of a way of doing that is think, well, what's the probabilities? Because probabilities, notice that right now we just got 0 and 1. Probabilities range from 0 to 1. And instead what we can do is estimate based on the probability that you're going to be a 1. So we can calculate P, that's the number, well, you can think of P as that number of people who have the outcome, the number of ones we have at each value, divided by the total number of people at that level. So for example, if we have 6 youth whose parents had 10 years of school and 2 of those dropped out, P would be 2 over 6. 2 dropped out of the 6. And now you see that's a probability, that's not an odds. It's 2 over the total of 6. And P will then vary across the range of our predictor variable. In fact, kind of here's how if we illustrate this. So these ones down here where almost everybody dropped out, their P's are 5, 6, or was it 4? Yeah, 5, 6. So you notice now, looking at the probability of dropping out across the range, and it makes intuitive sense. The more parent education, the lower the probability the child will drop out. And now we've got variability. We don't have the issue of nothing in between. But it still doesn't deal with the problem that asymptotes. I should have pointed that out. Well, actually, here, it's the next slide, I think, points it out. Because remember, P can't be less than 0, and probabilities can't be less than 0, and probabilities can't be greater than 1. So even if we don't have it, no matter how far you go, probabilities can never get less than 0. That's what I mean by an asymptote. It can get close to 0, it can get close to 1, but it can't cross it. So we still kind of have the same problem. Way down here, we're going to end up predicting negative probabilities. Numbers that don't make any sense. Or probabilities greater than 1. Again, numbers that don't make any sense. So probabilities help. We're doing a lot better in some degree, but it still is violating some of the fundamental assumptions for regression and giving us nonsensical results. And notice too, particularly here, when you get this sort of an asymptote where it starts to level off, that linear regression line is just going to get worse and worse and worse. It's kind of, in that sense, we talked about this with nonlinear we talked about this with curvilinear regression and that a few weeks ago. So what happens when you've kind of got some scores that are kind of, how do you model that? And you could put the curvilinear term is one way to kind of dance around it. You kind of curve around that plateau, but you still get that problem. And we definitely, and you can't get away from it here because we know whatever we do, those values can't get, probabilities can't ever get less than 0. So another approach would be, so we got two asymptotes. Can't be greater than 1, can't be less than 0. We could take those probabilities and convert them to odds. Yeah, almost. Need to take a break. I'll thank Shafin, she's signaling me to. You can convert them to odds, and that'll further improve it. Odds can go, because we've already seen the odds can be 50 over 50. Odds can be greater than 1. And all you do to make a probability in odds is just divide that probability divided by 1 minus. So take p minus over 1 minus p, makes it an odds. So instead now, looking at the probability for each value of x, we can look at the odds of a child dropping out. Okay? What we see with that, okay, so for example, we got 6 parents with 8 years of schooling. 5 of them dropped out, as we saw, kind of highly elevated. The 5, 6, our probability is 0.833 of dropping out. So the odds would be 0.833 over 1 minus 0.833, give us an odds of 5, which kind of makes sense. There's 5 to 1, right? That's what the odds are. 5 dropped out, 1 did not. So the odds are 5. We can kind of flip that, which is good to see with with the odds. If we look at parents with 14 years of schooling, we still have 6 parents, but now only 1 dropped out and 5 didn't. So it's the reverse. Instead of 5 dropping out and 1 not, we now have 1 drop out and 5 didn't. P is 1/6 or 0.1667. 1 minus p is 1 minus 0.667, gives us an odds of 0.2, 1 over 5, instead of 5 over 1. And you kind of see how they are reciprocal of each other. We can see odds can range from 0 to positive infinity. We saw odds can go greater than 5. Odds can't get less than 0 because this can, you can never get a negative number in there. But odds can range from 0 to positive infinity. If we now plot those odds instead of the probabilities, it's getting better. You notice now we don't have that upper asymptote, but we still have this problem of, negative odds. And we completely kind of go off the rails at this lower end, at this one end. And we're not, again, able to model what's going on with that asymptote. Okay, let's take a break there, and then we'll come back with the definitive solution.